Hello all and welcome to our final video on our dive into integration. As we can see here by the title, this is a video on the applications of integration. Now I want to make it really clear that this is a sort of superficial look at integration, and there are significantly more things that you can do with it that are actually quite useful. Unfortunately we don't cover it as part of the 12 methods course. But do be warned, if you go on to sort of studying mathematics at higher levels at university, it'll come up a lot, especially in engineering and sciences. It's really quite useful. But right, we'll jump straight into it. So the first thing that we can find from integration is an average value of a function. So this is the formula here that gives us our average value. The way you can think of it that this works is realize that when we integrate, we're finding the area under the curve, and you could think of it we're summing every single value. Okay, we're technically finding back towards differentiation as you're letting the limit approach zero, is we're technically summing infinitesimally small gaps of every value. So if we're adding all those values up together, we could find the average of those by effectively dividing by how many values there are, which is what this bit here is saying. That's effectively, let's get the integration gives us all our values, and then we're going to divide that by how many values there are. How many values there are, and well, how many values are there? Well, it's the furthest right point. Let's just put in some numbers here to make this a bit more concrete. Let's say this is 7 and this is 1. Well, we've got effectively 6 worth of values that are being summed. So if we just put 1 on out the front, the other way that might be a little bit easy to think of this rule is technically a, b, f of x with regards to x divided by b take a. That might make a little bit more sense when you see it that way. But it's technically the integration sums every single value, and if we want to find the average of them, we just have to divide by how many values there are, which in our case is b take away a, or 7 take away 1. But yeah, that's the formula. You can also think of it as it's got this description here. It's finding the average value. It would find also the area of the rectangle, that if we take this area up here and bring it into here, and we're having to take some of this area here, it's finding technically the height of that rectangle that would have the same area if it was just flattened out. But let's get straight into it. So find the average value find the average value for the function defined by f of x is equal to sine of 2x for the interval between pi on 8 and 3 pi on 8. So we just said that the average value is equal to 1 on, and this is a, that's b, so we've got 3 pi on 8 take away pi on 8. And I'll just write the equation up here again, just for reference. B take a integral b to a of x dx. The average value is equal to that. So integral of sine of 2x respect to x, and we're going between 3 pi on 8 and pi on 8. So that is going to be equal to, well, let's just do one line where we're going to, let's use proper notation, is equal to 1 on 3 pi on 8, take away pi on 8 is just 2 pi on 8, and we can do the integral at the moment. So if you check your formula sheet, the integral of sine a of x is equal to negative 1 on a sine cos ax, where the a is the coefficient inside the sine, So we can make this as 1 on 2 equals 2x, and again we're between 3 pi on 8 and pi on 8. So 1 on 2 pi on 8, that's remembering just 1 on 2. Dividing by fractions is the same as multiplying by the reciprocal. So that would just be equal to 4 on pi. So this just turns into 4 on pi at the front. And now we can substitute in our terminals. So we're going to get negative half of cos 2 times by 3 pi on 8. Take away negative half. Let's put that in there. Cos 2 by pi on 8, okay, which is equal to 4 on pi. And now let's just start simplifying stuff. 2 times 3 pi on 8 becomes 6 pi on 8, which is the same as 3 pi on 4. Plus, if we bring the two negative signs together, we're now getting plus half of cos pi on 4, simplifying that. And minus half. So now we can do circular functions. Let's have a think about pi on 4. So pi on 4 is there. And cos is finding the horizontal component of that. So that would be equal to root 2 on 2, if we remember our exact values. And then 3 pi on 4 is over here. Okay, so same thing, we're finding a horizontal component. So that is negative root 2 on 2. Because it's over in the second quadrant, that's a negative x value. So we get cos for negative, so that's going to be negative root 2 on 2 plus half by root 2 on 2. We get negative 4 on pi. That's going to be root 2 on 4 plus root 2 on 4. So we're going to get 4 on pi at 2 root 2 on 4. And I'm going to then cancel that with that. So we finally get 2 root 2 on pi. So that's our average value between those two terminals. So the only bit of integration is, well, our normal substitute, doing our integration and then substituting in our terminals. The rest of it is actually calling on other topics with solving circular functions. But there's an example of using that average rule. Right, the other bit of applications that we do in Year 12 methods is motion in a straight line. So if you remember from chapter 10, which is our applications of differentiation, and I keep encouraging this, we always want to think of when we get the derivative, we're getting the gradient, but we think of it's technically the rate of change of whatever function we're differentiating. So if we start with a function that gives us our position, and we always refer to position as x, if we differentiate that, we're going to get some function that tells us the rate of change, and I'm going to keep saying this word over and over and over, rate of change of position. So what is the rate of change of position? Well, that is our velocity. Okay? And then, so if you do the differentiation, you'll be able to see that you get that. And we've now got a rule that tells us velocity, and we use v to represent velocity. It's still with respect to time, so we're going to be using t as our variable for time in all of these to avoid confusion with the x of position. Right, so what happens if we then differentiate the velocity function? Well, same thing, we're going to get the rate of change, but this time our new function is going to tell us the rate of change of velocity, because that's what we were differentiating. We're differentiating velocity. And what does that give us? Well, the rate of change of velocity is called acceleration. And we get a new function that we call A for acceleration. Well, that's all differentiation. We can use integration because we know the indefinite integral gives us the antiderivative. It's just the process of going effectively backwards or in reverse. So we get this. If we start with acceleration, we can integrate it, and we're going to get velocity because that's just the differentiation in reverse. Same thing, if we then have an equation for velocity, we can integrate it, and we're going to get something new, which will tell us the position. The one thing that's not shown in this slide is technically we have to have a plus c, but a lot of time you'll be given information about the particle or whatever it is that's moving that you'll be able to figure out what that c is. And then again, when you integrate, you'll get another new plus c, so let's maybe call this plus d. But again, you'll be given some information about the position of its particle at some time that will allow you to figure out what that d value is. So saying all that, the takeaway from this is, if we think of differentiation of giving us rates of change, well, then we can obviously work backwards to go from acceleration to velocity and then velocity to position. So let's jump straight into this problem. Now, this problem has a lot of parts to it. We've got A, B, C, D, E, F. There's a lot there. So how are we going for time? 11 minutes. So this is going to probably go a little long. Put me at 1.5 times speed if need be. Okay. So a particle is moving in a straight line, has an acceleration of 3 minus 2t meters per second squared. So this is our equation for acceleration, is equal to 3 minus 2t times seconds. T needs to be greater than or equal to 0. So we've got a domain here that we want to pay attention to. We've got a restriction. If the particle starts at the origin, so that's another thing that tells us that when t is equal to 0, its position, which is x, is also equal to 0. And it has a velocity of 4 meters per second. So again, when it's at the starting point or starting time, t is equal to 0, v is equal to 4. So that'll be handy. That's what we call initial conditions. Gives us some data about the point. So find the time when the particle comes to rest. So when the particle comes to rest, that must mean the velocity is equal to 0. So this is in none of the information we're given, but we are given an acceleration equation, so I can anti-differentiate it to get a velocity equation, and then I can sub this idea in to find what time that would occur at. So velocity is going to be equal to the antiderivative of the acceleration equation with respect to time, which is equal to the antiderivative of 3 minus 2t with respect to time, which gives us 3t minus t squared. Because just to show where the t squared comes from, we have 2t, add 1 to the power, divide by the power, 2's cancel. We just get t squared. Cool. So we want to know when the particle comes to rest. Like we said, that means the velocity has to be to 0. So we're going to let v equal to 0. So it follows on. Ooh, and I've made a mistake. I forgot plus c. Plus c. So I can't find v yet. Okay, we need to differentiate, and this is why we need to be careful. We have our plus c. So how do we find that? Well, we were told when time is equal to 0, velocity was equal to 4. So I'm going to sub in 0, 4. That's our time, that's our velocity. So we get 4 is equal to 3 by 0, 0 squared plus c. So it is obvious that c is equal to 4. Now we have the proper equation for velocity, which is 3t minus t squared plus 4. So we can come up now and go, like I said before, we're going to let the velocity equal to 0 to find what time that occurs. So we get 0 is equal to, let's write it in the regular quadratic order, plus 3t plus 4. I'm going to take the negative out as a common factor just to make factorization via inspection a little bit easier. So we can effectively ignore that negative sign out the front now when we're factorizing just this bit. So t, 2 numbers to multiply give me -4 and add to give me -3. That's going to be -4 and +1. And then we can use the null factor law. We don't have to care about, again, this negative out the front, because even if we say we could just divide everything by -1, divide by -1, it cancels out, disappears. The null factor law still applies, that with that negative in there, that means either that or that has to be 0. So we get t minus 4 is equal to 0, or t plus 1 is equal to 0. So we get t is equal to 4. T is equal to -1. This is outside the domain, which is why I highlighted this before. Whenever you're given sort of information like that, may as well make a note of it. Hopefully that then means you rings a bell once you find some values. So the particle is stationary. This is an applied problem, so we generally want to answer in words. Stationary when time is equal to 4. For those of you doing physics, this will be the idea of the connections between acceleration, velocity, and position will help a little bit. But if you aren't doing physics, go back to these two charts and have a look through the connections. Right, so what have we done? We have found an equation that tells us our velocity. We know that and we've got a bunch of initial conditions. So let's keep going. Sketch the graph of v of t, found in part A, over the duration of the particle's movement. You must include all intercepts and stationary points. Okay, so we had our domain t must be greater than 0, and we figured out that velocity was equal to -t squared plus 3t plus 4. And we found, okay, the velocity was equal to 0 at 4 and -1. So we can interpret that. That's effectively our intercepts, because this is time. Time is our x-axis, velocity is our y-axis. And that velocity was 0, or v is equal to 0, at t is equal to -1 and t is equal to 4. 1, 2, 4. So there. Okay, I'm going to leave this -1 even though it's outside the domain just for now to help with a bit of shape. We can see that the gap there is 5 units. So that means the turning point needs to be the halfway point. So 4 take away -1 on 2 happens to be 5 on 2. No, sorry, that needs to be a plus in there. There we go, just 3 on 2, the average of it. So the turning point is halfway, so that's at 1.5, or 3 on 2. So because we're asked to find, must include all intercepts and stationary points. Another bit of information actually before I put in this turning point we had was this one here. When time is equal to 0, v is equal to 4. So straight away we can put that on our graph as well. T is 0, velocity is 4. So we've got that point there, 0, 4. Turning point occurs at 3 on 2. So I just want to find what the velocity is at that. So the velocity at 3 on 2 is equal to -3 on 2 squared plus 3 by 3 on 2 plus 4 is equal to -9 on 4 plus 9 on 4 plus 4, oh no, plus 9 on 2 is equal to -9 on 4 plus 18 on 4 plus 16 on 4 is equal to negative 9 plus 18 is positive 9 plus 16 is 25. So we get 25 on 4, which is 6 1/4. So about there. So there's our turning point there. Let's put that one in blue. Okay, so that is 3 on 2, 25 on 4. And we should be able to sketch our graph. So put the turning point in, come down. Oh, that line at the end is not great. It goes past. Oh, that's even worse. There we go. That is 4, 0. And come back in. And we already have that point labeled. And that's it. And like I said, we could see that it obviously goes down to that dot, but since time needs to be greater than 0, we're not going to include that. And I might even just erase that. Cool. So we can now see the graph of the velocity. So let's think of what this means story-wise of the particle. Here, the velocity is 4. That means it's moving fast. And the velocity is going up. And up here it's 6 1/4 meters per second. So that means through this stage here it's accelerating. And because it's positive velocity, that means it's going to the right. Positive value means going to the right normally. Now here, along this side, we can see our velocity is reducing. It is still positive. Like here, the velocity is 6, here is 5, here is 4, here it is 3, here is 2, here is 1. So it still has positive velocity values, but those values are getting lower. So that means it is decelerating. So I can't spell tonight. Okay. But that's just something to be aware of, that we're accelerating, we get to maximum velocity, and then we start decelerating. Cool. So that's really, really handy, just having a context of the problem. As soon as you get the graph, actually have a look at it and think, what does this mean? What can I know? What story-wise? Okay, let's keep going. The particle moving in a straight line has an acceleration, blah, blah, blah. So given the displacement of the object is the area under a velocity time graph, find the position of the particle at the instant it comes to rest. Okay, so we need to know when it comes to rest, which means its velocity is 0, which is down here. So we know comes to rest, v is equal to 0 at time is equal to 4. So we want to find this displacement, which we know we can get the displacement by integrating, finding the area as it says here under a velocity time graph of the velocity function with respect to time. So x is going to equal to the antiderivative of, what do we have, negative t squared plus 3t plus 4. This is the equation that we found previously. Right. The advantage of this problem is that our particle, our journey technically starts at time equals 0. So we don't have to really technically, and in general, if you just want to find the position at a given time, you don't need to worry about terminals, because this equation tells you x is displacement, its position at any given time. So we can just find the indefinite integral. So we get negative t cubed on 3 plus 3t squared on 2 plus 4t plus c. I've remembered this time. And how can we find that plus c? Okay. The particle starts at the origin. Okay, so the origin means that its displacement is 0 at time is equal to 0. Which, if we sub that in, it's pretty obvious that everything t's of 0 means every term becomes 0. And since x is 0, that must mean c is 0. So c is equal to 0. So we get x is equal to negative t cubed on 3 plus 3t squared on 2 plus 4t. Now we want to find when it comes to rest, which this time is equal to 4. So x of 4 is equal to negative 4 cubed on 3 plus 3t squared on 2 plus 4. Let's do that. Plus 4 by 4. There we go. Okay, 4 cubed is 60. 16 on times by 4. 64. Negative 64 on 3 plus 16 by 3 is 48. So we get 48 on 2 plus 16. So we're going to get 48 on 2 is 24. So I'm just trying to convert these to all be on 3. May as well convert it to a whole number, and then 24 is the same as on 3 times that 3, 4 is 8. No, 3, 4 is 12. 3, 2, 6, 7, 72. So that becomes 72 on 3. Negative 64 on 3 plus 72 on 3. 16 times by 3. 3 6s 18. 3 1s 48. So plus 48 on 3. That is all going to become negative 64 plus 72 is 8. 8 plus 48 is 56 on 3. There we go, which is what, position-wise, as a mixed number? 18 and 1/3 meters. Yes, we were dealing with meters per second, so there we go. Find the acceleration at this instant. So again, we're just dealing with at time equals 4. So a of 4, and the acceleration equation we were given at the very start is equal to 3 minus 2 by 4, equal to 3 minus 8 is equal to negative 5. And the units for acceleration, as we're told there, is meters per second squared. Or for those of you doing physics, we'll be used to writing it as negative 5 meters per second to the negative 2. There we go. Okay. And we got 2 more bits. 27 minutes. Apologise for the length, but hey, it's an application problem. May as well work it all the way through. Particle moving in a straight line has, that's all the same information. Find when the acceleration is 0. So we just need to find when a is equal to 0. So we're going to let a equal to 0, which means 0 is equal to 3 minus 2t. So we get 2t is equal to 3, so t is equal to 3 on 2 seconds. Okay, which makes sense. If we go back to this picture, okay, this point here, this turning point, at that point, the rate of change of velocity, we think of the, now if we're thinking of derivatives, the rate of change of velocity at a turning point is 0, the gradient is 0, so that means at the turning point, a is equal to 0, which we figured out was 3 on 2 there, from here. So that matches up. That makes sense. Find the velocity at that time. So we just need to find the velocity at 3 on 2 using our velocity equation, which we have here. Negative t cubed on 3. Let's just do t at the moment. Plus 3t squared on 2 plus 4t. Okay. So v of 3 on 2 is equal to, and we can substitute it all in, okay, but we've done this work. We did it when we had to find the turning point. We did it all here. Okay. So we figured out it was 6 1/4 or 25 on 4. Let's go with 25 on 4. 25 on 4 meters per second. Or you can write it that way. And that's it. So that's it for the video. So the two main, I guess, takeaways from this is that, let's do takeaways, is the average value equation. Please note that you aren't given that in the methods formula sheet. So you do have to come up with a way of remembering that. And then the other one is the connections between acceleration, velocity, and displacement. I should say, not position, displacement. Rightio, that's it. Have a good evening and see you in class. As always, if you have any questions, put it in the comments below or hit me up via email. Thanks and see ya.